When it comes to speed, military aviation has always chased the dream of building the fastest aircraft in the world. But the race for hypersonic flight isn't led by the United States alone. Russia's fastest fighter jet has been turning heads for years. What makes this aircraft so remarkable? And what hidden capabilities set it apart from the rest? Join us as we explore the capabilities of the Russian fastest fighter jet that shocked both America and China. The MiG-25 was not just another Soviet jet. It was born out of fear, an urgent fear that gripped Soviet generals in the late 1950s. At the time, the United States was showing off a new generation of supersonic bombers that could fly faster and higher than anything the Soviets had in their arsenal. First came the B-58 Hustler, an American bomber capable of flying at twice the speed of sound, or Mach 2. But what really alarmed the Kremlin was the XB-70 Valkyrie, a futuristic aircraft designed to cruise at Mach 3 speeds, 3 times the speed of sound, while flying at altitudes above 70,000 feet. From those heights and at that velocity, the Valkyrie could slip past Soviet air defenses and unleash nuclear weapons before anyone could stop it. The Soviet Air Defense Forces, known as the PVO, quickly realized their existing interceptor jets were useless against such a threat. None of them could fly high enough or fast enough to even catch sight of the Valkyrie, let alone shoot it down. For the Soviet Union, this was not just a military problem, it was a national security nightmare. In desperation, the government handed the challenge to the Mikoyan-Gurevich Design Bureau, the same team responsible for earlier MiG fighters. Their mission was simple to describe, but nearly impossible to achieve. Build a jet that could climb like a rocket, reach extreme altitudes, and fly at blistering speeds to catch and destroy American bombers before they dropped their deadly cargo. By the early 1960s, the project was officially approved. It was given the name YA-155, which would eventually split into 2 versions. The YA-155P would serve as the dedicated interceptor, while the YA-155R would act as a high-altitude reconnaissance aircraft. Both shared the same extreme design philosophy: speed and altitude above everything else. The MiG-25 was never meant to be a nimble dogfighter like later jets. Agility and long combat endurance did not matter for its mission. What mattered was raw performance. It needed to take off, rocket into the sky, and intercept intruding bombers in a matter of minutes. Think of it less like a graceful fighter and more like a guided missile with a cockpit. This extreme focus on performance shaped every part of the aircraft. It was built largely from nickel-steel alloys instead of lighter aluminum, since lighter metals would melt at the scorching temperatures caused by Mach 3 speeds. Its engines were massive and powerful, designed to push the aircraft at breathtaking velocity, even if they guzzled fuel at alarming rates. The MiG-25's mission profile was brutally simple: race toward the target at incredible speed, fire its missiles in a high-speed pass, and then return to base. There would be no circling battles, no extended patrols, and no flashy aerobatics. It was a specialist, built to counter one of the scariest threats of the Cold War. When Viktor Belenko's MiG-25P was taken apart by Western experts in Japan, the results stunned them. For years, the West had feared it was an advanced titanium superfighter capable of leaving every other jet behind. Instead, what they uncovered was a machine built with raw practicality, focused more on sheer performance than on refined craftsmanship. The most surprising discovery was its construction. Roughly 80% of the airframe was not crafted from lightweight alloys or futuristic titanium, but from arc-welded nickel steel. This choice seemed almost crude to Western eyes, but it was in fact a practical solution to a serious problem. At sustained speeds approaching Mach 2.8 and beyond, the skin of the aircraft would heat up to extraordinary temperatures. While titanium would have been an ideal material to resist such heat, the Soviet Union did not have the ability to produce it in the massive quantities required for such a project. Instead, steel was chosen because it was both available and strong enough to withstand the brutal thermal stress. This decision, however, came with enormous consequences. The aircraft was incredibly heavy compared to its Western counterparts. Its empty weight was around 20,000 kilograms, or approximately 44,000 pounds. To get such a heavy jet into the sky and keep it there, the designers had no choice but to give it enormous wings. These oversized wings created the necessary lift to support the steel frame, even if they made the jet look less sleek than other fighters of its time. Instead of smooth, polished panels like those on American aircraft, the MiG-25 revealed exposed rivet heads, rough welding seams, and visible signs of hand-built work. To experts used to precision assembly lines and elegant finishes, the Soviet aircraft looked rugged and unfinished. Some even described it as crude, a far cry from the advanced flying machines they had imagined. But what seemed unsophisticated on the surface was actually a clever reflection of Soviet design philosophy. The MiG-25 was never built to win beauty contests or impress with refined details. It was created to do one thing: fly at blistering speeds and extreme altitudes in order to intercept and destroy enemy bombers before they reach their targets. Every design decision, from the heavy steel body to the massive wings, was aimed at making this single mission possible. In a way, the MiG-25 was like a sledgehammer. It lacked finesse, but delivered devastating force in exactly the way it was intended. While Western engineers might have frowned at its rough look, they could not ignore the genius behind its practicality. The Soviets had accepted weight, sacrificed elegance, and ignored agility in order to gain strength, speed, and survivability. In the process, they created a jet that was raw, brutal, and unforgettable. Powering the mighty MiG-25 were two gigantic Tumansky R-15 B-300 single-shaft afterburning turbojets. These engines were enormous pieces of engineering, designed less for elegance and more for brute force. They produced astonishing power, with each engine generating close to 110 kilonewtons of thrust when using an afterburner. To put it in simpler terms, that was nearly 25,000 pounds of thrust per engine, enough to lift and push the massive Foxbat into the upper limits of the stratosphere. This raw force allowed the aircraft to sustain speeds of almost Mach 2.83 during normal operations. Such speeds were beyond what most Western aircraft could achieve in the same era, and they cemented the Foxbat's reputation as one of the fastest jets ever built. Yet there was always the legend of its fabled top speed, Mach 3.2. This incredible figure captured imaginations and spread fear among potential adversaries. However, reaching that speed was never intended for regular missions. In fact, it was only allowed under extreme emergency situations. Pushing the MiG-25 that far would cause the engines to run far hotter than their safe limits. The extreme heat would quickly begin to damage the internal components, meaning the engines would essentially burn themselves out if the pilot held that speed for too long. In other words, it was like having a self-destruct button hidden within the power plant, and Soviet engineers strictly forbade such recklessness outside of absolute necessity. As with all feats of extreme performance, there was a steep price to pay. The Foxbat's engines were incredibly thirsty. They consumed fuel at an alarming rate, particularly when flying at low altitudes where the efficiency dropped even further. This was not just a small drawback. It became one of the aircraft's defining weaknesses. Western pilots and engineers even nicknamed the Foxbat a gas guzzler, and the name was not far from the truth. While the jet could climb to incredible heights and outrun nearly anything in the sky, it could not stay airborne for very long without refueling. The limited efficiency of the R-15 engines severely reduced the fighter's combat radius. At best, the Foxbat could manage only a few hundred miles before needing to return or meet up with a tanker. This meant the aircraft was never suited for long-distance patrol missions or extended dogfights. Instead, its role was shaped by this limitation. It was designed to be a short-dash interceptor. The MiG-25's main job was to take off quickly, climb at an astonishing rate, reach extreme altitude and speed, intercept its target, and then return to base before its fuel tanks ran dry. This made it a very specialized machine, superb in its intended role, but limited if pushed beyond it. Despite these drawbacks, the Foxbat's sheer speed and altitude performance gave it a fearsome reputation in the Cold War skies. Its very existence forced rival nations to rethink their strategies and technologies, proving that raw power, even when paired with inefficiency, could still reshape the balance of air superiority. From its very first flights, it stunned the aviation world by setting world records that seemed almost unreal at the time. The aircraft soared higher and faster than anything most nations had ever seen, reaching an astonishing altitude of more than 37,000 meters in a zoom climb, which translated to over 123,000 feet. Such feats carved the MiG-25 into the history books as one of the fastest and highest-flying combat aircraft ever designed. Yet beneath this extraordinary ceiling of performance lay glaring weaknesses that made the aircraft something of a paradox. Its structure, built primarily from heavy stainless steel rather than lighter alloys, meant that agility was sacrificed for raw speed and strength. In combat, this limitation was clear. The MiG-25 was restricted to a modest 4.5 Gs. Against agile Western fighters like the American F-4 Phantom, this was a crippling flaw. In a turning battle, the Fox-Bat quickly found itself outmaneuvered, its pilot trapped in a machine designed for climbing and sprinting rather than twisting and dodging. The story became even more troubling at low altitudes. While the MiG-25 had been perfected for thin air at extreme heights, it was cumbersome closer to the ground. The thick atmosphere exposed its weaknesses, with its wings struggling to generate efficient lift and its engines burning through fuel at an alarming rate. At these levels, the fighter could no longer rely on its high-speed edge, leaving it clumsy and vulnerable to opponents built for flexibility across a wider range of conditions. The combat systems of the MiG-25 mirrored the aircraft itself, impressive on paper, yet flawed in real battles. Its radar was one of the largest and most powerful ever fitted to a fighter, capable of detecting targets from astonishing distances. But this strength came with major drawbacks. The radar emitted so much energy that it practically announced the aircraft's presence long before it could engage its prey, robbing it of the element of surprise. Moreover, the early missiles carried by the Fox-Bat were massive and designed primarily for high-altitude interception. They were deadly against bombers flying high and straight, but far less useful against nimble fighters that darted and weaved. Even so, the Fox-Bat was not without its strategic value. It terrified adversaries by simply existing. Western intelligence in the 1960s and 1970s often overestimated its capabilities, believing it to be nearly unstoppable. This forced the United States to accelerate the development of fighters like the F-15 Eagle, which eventually surpassed the MiG-25 in maneuverability and versatility. In this sense, the Fox-Bat shaped the global fighter race, not through direct dominance, but through the fear it inspired. Much of its reputation rested not only on raw speed and altitude, but also on the powerful electronics packed inside. At the heart of this beast was its radar, an instrument that revealed both the brilliance and the brute force approach of Soviet design. At the core of the MiG-25P interceptor was the RP-25 Smerch-A radar, which NATO codenamed Foxfire. This system stood among the most powerful airborne radars of its time. It relied on older but tough vacuum tube electronics, producing such immense energy that it could pierce through enemy bomber jamming attempts. Its detection range against a bomber-sized target reached up to 100 kilometers, making it a formidable piece of equipment in high-altitude combat scenarios. Yet despite its raw power, the Smerch-A carried a fatal weakness. It lacked look-down/shoot-down capability. This meant the radar could not tell the difference between a low-flying aircraft and the clutter of the earth below. In effect, it became nearly useless when tracking targets at lower altitudes. This limitation proved disastrous, since by the time the MiG-25 was introduced, NATO had already shifted its strategy. Instead of relying on high-altitude bombing runs, Western forces increasingly turned to low-level penetration tactics, deploying both bombers and cruise missiles that could sneak under radar coverage. The Fox-Bat, built to counter threats of an earlier era, suddenly found itself mismatched against modern methods of attack. When it came to weaponry, the MiG-25 was armed with the massive R-40 missile, which NATO referred to as the AA-6 Acrid. 4 of these heavy weapons were carried under the interceptor's wings, making them the centerpiece of the aircraft's arsenal. Much like the aircraft itself, these missiles were tailored for the high-altitude interception role rather than flexible dogfighting. The R-40 came in 2 primary variants, the radar-guided R-40R and the heat-seeking R-40T. Each missile was built with a very specific purpose, bringing down large, strategic targets flying at great heights. Their performance reflected this goal, With a range stretching up to 80 kilometers and a massive 100-kilogram warhead, the R-40 was engineered to obliterate heavy bombers in a single strike. Against such non-maneuvering aircraft, it was lethal. However, the limitations appeared once the Fox-Bat faced more agile opponents. Fighters designed for speed and maneuverability could outmatch the Acrid's bulky design and less responsive guidance system. In close encounters or against nimble aircraft, the missile's effectiveness dropped sharply. The Fox-Bat was simply never meant to duel modern fighters. Its size, power, and weapons all pointed to a very narrow mission set, destroying bombers before they could reach Soviet skies. The combination of the Smerche radar and the R-40 missiles highlighted the strengths and weaknesses of the MiG-25. On one hand, it could deliver an immense destructive force at high altitude, creating a real deterrent for any bomber attempting to breach Soviet defenses. On the other hand, the interceptor's rigid specialization left it exposed to evolving tactics. By the 1970s, Western air forces were fielding planes capable of flying low and fast, exactly where the Fox-Bat's radar could not function effectively. And yet, numbers and specifications only tell part of the tale. To see the MiG-25 for what it truly was, you have to follow it into battle. Its combat record paints a vivid picture, one of dazzling speed and altitude, but also of the unforgiving limits that no amount of raw power could escape. The combat story of the MiG-25 is as fascinating as the machine itself, a mix of brilliance, fear, and harsh reality. It was a jet that could soar higher and faster than almost anything in the sky, and that alone made it a psychological weapon. But when it faced the test of modern air combat, its strengths and weaknesses became impossible to hide. In the early 1970s, the MiG-25R reconnaissance version first showed its worth in the hot skies of the Middle East. Soviet pilots flying for Egypt took their Fox-Bats over the Sinai Peninsula, then held by Israel. They blasted through the sky at altitudes no Israeli Phantom could touch, and at speeds that left pursuers helpless. Cameras clicked away as the aircraft roared overhead, gathering priceless intelligence while the defenders below could only look up in frustration. For the Soviets, it was the perfect showcase of the Fox-Bat's reconnaissance power, fast, untouchable, and unchallenged. Not long after, India also put the MiG-25 to good use. Its MiG-25 RBS routinely crossed into Pakistani skies, photographing military sites deep inside enemy territory. Pakistani defenses had no answer. The flights were so one-sided that the aircraft earned a nickname among Indian pilots, the Pradhan, or Prime Minister, because it could go anywhere it pleased. During the brutal Iran-Iraq War of the 1980s, the Fox-Bat played a more aggressive role. Iraqi pilots flew it not only as an interceptor, but also as a bomber. They claimed kills against Iranian F-4 Phantoms and nimble F-5 fighters, proving that, in the right hands, the aircraft could still be lethal. It was during this war that the Fox-Bat earned a reputation as both a hammer and a scalpel, capable of smashing targets from above or piercing enemy air defenses in daring missions. But the Gulf War of 1991 brought the MiG-25 into direct combat with the most advanced fighters in the world. On the very first night of the war, an Iraqi Fox-Bat scored a shocking victory. A MiG-25 PD launched a missile and destroyed a U.S. Navy F/A-18C Hornet, one of the few air-to-air victories scored by Iraq in the entire conflict. For a brief moment, the old interceptor had reminded the world why it had once been so feared. Later in that same war came the legendary Samura air battle. Two Iraqi Fox-Bats were vectored against two American F/A-15Cs. At beyond visual range, both sides fired missiles in a tense duel that echoed the Cold War nightmares of superpower clashes. When the smoke cleared, neither side had lost an aircraft. It was a tactical draw, but symbolically it was stunning. Even a struggling Air Force could, with the Fox-Bat, challenge America's premier air superiority fighter. Still, the war also showed the aircraft's limits. Several Iraqi MiG-25s were destroyed by American FAR-15s, proving that the Fox-Bat's sheer speed could not always save it in modern combat. And in 1992, history was made when a US F-16 shot down an Iraqi Fox-Bat with the brand new AIM-120 AMRAAM missile, the very first air-to-air kill ever achieved with that weapon. Russia's deadly secret just took flight, NATO was completely taken unaware, while Russian engineers quietly turned their Su-57 fighter into something far more dangerous, a machine packed with sixth-generation technology that could change war forever. Is this Russia's greatest military breakthrough in decades, or the most desperate lie ever told? Join us as we find out every secret about the Russian sixth-generation fighter jet. Inside Russian airspace, 8 Su-57 prototypes have been flying missions that NATO never saw coming. These weren't ordinary test flights. According to Vladimir Mikheyev, a top advisor at Rostec Corporation, Russia has been secretly installing sixth-generation fighter components onto its existing fifth-generation platform. The testing began quietly in 2023, with new flight and navigation systems appearing on the PAKFA prototypes. Russian engineers weren't just upgrading software. They were rebuilding the aircraft's electronic warfare capabilities from the ground up. The new radar system operates as both a detection device and a reconnaissance tool, while the electronic warfare suite can track and jam enemy signals simultaneously. Over 700 test flights have validated these modifications, according to Sukhoi officials. Each mission collected data on how tomorrow's fighter technology performs in today's aircraft. The results have sent shockwaves through Western intelligence agencies. NATO's concern stems from a simple fact. Russia appears to be leapfrogging traditional development timelines. While American and European programs like NGAD and FCES are still on the drawing boards, Russia claims to have working sixth-generation components flying right now. The implications are staggering. If Russia's claims prove accurate, they've achieved technological parity with the United States years ahead of schedule. The Unified Electronic Warfare System alone represents a major advancement in combat networking, the ability for aircraft to share information and coordinate attacks in real time. But the most troubling development involves the aircraft's dual-mode capability. Russian officials have confirmed the sixth-generation platform will operate both manned and unmanned. This means enemy forces could face swarms of autonomous fighters working alongside human pilots, creating tactical scenarios no current defense system was designed to handle. The testing has also revealed advances in engine technology that could reshape aerial warfare. The new power plant delivers significantly higher thrust while consuming less fuel, a combination that extends operational range and reduces logistical vulnerabilities. This efficiency breakthrough allows the aircraft to perform supersonic maneuvers at extended distances without frequent refueling. Western analysts remain skeptical about Russia's timeline claims. The head of Sukhoi's design bureau stated the first true sixth-generation aircraft could take flight in the second half of the 2020s, suggesting current tests are preliminary rather than operational. However, the Advanced Research Foundation in Moscow has been working on multiple sixth-generation projects since 2014, focusing specifically on materials and engine development in cooperation with the consulting firm Lyulka. This parallel development track suggests Russia's sixth-generation program runs deeper than public statements indicate. The secrecy surrounding these tests has intensified geopolitical tensions. China's BIDE program and America's NGAD initiative suddenly face a competitor that may have achieved critical breakthroughs first. The global balance of air power, unchanged since the introduction of stealth technology in the 1990s, could shift dramatically if Russia's claims prove legitimate. NATO intelligence agencies are scrambling to verify the extent of Russia's technological advancement. Satellite imagery and electronic intelligence gathering have intensified around Russian test facilities, but confirming the true capabilities of these modified Su-57s remains extremely difficult. The stakes couldn't be higher. Air superiority has determined the outcome of every major conflict since World War II. If Russia has genuinely integrated sixth-generation technology into operational aircraft, the military balance that has maintained global stability for decades may be crumbling. But these secret tests revealed something far more chilling than upgraded radars and better engines. What happens when artificial intelligence takes control of warfare? Russia is secretly testing new versions of its Su-57 fighter jets, and they're not just upgrading hardware, they're experimenting with systems that let the plane make decisions without a pilot. These jets are using artificial intelligence to spot, track, and even attack targets on their own. This changes everything. In normal air combat, pilots rely on training and quick reflexes. But now these new systems can process information way faster than any human, deciding the best way to attack or dodge in just milliseconds. Tests show the AI can handle multiple enemies at once and even work with other planes during a mission. Russia's bigger plan is to pair human pilots with autonomous drones. One fighter jet could control up to 4 unmanned wingmen, flying in attack formations designed to overwhelm any defense. They're also pushing for hypersonic speeds, faster than 5 times the speed of sound. If successful, these jets could hit targets anywhere on Earth in about 2 hours. At that speed, most current defense systems wouldn't even see the attack coming. Stealth technology is also advancing. These planes aren't just hard to spot on radar, they're designed to avoid being seen by heat sensors, visual detection, and even newer surveillance systems. Russian scientists are working on special materials that help the jet blend into its surroundings. One of the most controversial parts is that these new systems can choose and hit targets on their own, without a human making the final decision. That's raising big ethical concerns around the world. While the United States and its allies are focused on keeping pilots in control, Russia seems to be racing toward full autonomy. And they're moving fast. Instead of building new jets from scratch, Russia is testing new tech on old models, which is saving them time and speeding up development. Meanwhile, Western programs like Europe's FCAS or Japan and the UK's GCAP are moving more slowly due to international partnerships and government red tape. Russia's centralized control gives it an edge in decision-making and execution. China is also in the race, working on its 6th-generation jet with different priorities, creating a 3-way global competition in future air power. These new jets won't just fight other planes, they might be able to shut down satellites, block enemy communications, and carry out a cyber attack, all without firing a single missile. In effect, they're flying computers that can disrupt entire military networks. Russia's tests show these fighters might even act like command centers in the sky, managing operations and blocking enemy responses all at once. Put simply, the mix of AI, hypersonic speed, and autonomous weapons is changing air warfare forever. Old strategies may no longer work in a world where machines fight faster, smarter, and without warning. While Russia experiments with tomorrow's weapons today, the rest of the world races to catch up. Who will control the skies of 2030? Russia's accelerated 6th-generation testing has triggered the most intense aerospace competition since the Cold War. While Western programs remain years from first flight, Moscow aims to deploy operational 6th-generation capabilities by 2030, a timeline that has defense planners from Washington to Tokyo scrambling to respond. The Russian strategy differs fundamentally from Western approaches. Instead of developing entirely new aircraft from scratch, Russia integrates advanced systems into existing platforms, validating technologies through real flight testing rather than computer simulations. This pragmatic method has compressed traditional development cycles from decades to years. America's next-generation air dominance program, by contrast, remains locked in conceptual phases. NGAD focuses on air superiority platforms designed to penetrate heavily defended airspace, but the program has faced repeated delays and budget constraints. Current projections suggest American 6th-generation fighters won't enter service until the mid-2030s, potentially 5 years behind Russian deployment. The technological gap widens when examining production philosophies. Russian defense contractors operate under centralized direction, enabling rapid resource allocation and decision-making. American programs must navigate congressional oversight, contractor competition, and bureaucratic approval processes that slow development at every stage. Europe's response has been equally fragmented. The Future Combat Air System, jointly developed by France, Germany, and Spain, aims for operational deployment by 2040. However, disagreements over workshare, technology transfer, and program leadership have created delays that push meaningful progress even further into the future. Britain's collaboration with Japan and Italy through the Global Combat Air Program offers more promise, targeting service entry in the early 2030s. This program emphasizes artificial intelligence and autonomous systems, potentially creating capabilities that rival Russian developments. But international coordination challenges remain significant obstacles to meeting ambitious timelines. China's Baidu program adds complexity to global calculations. Intelligence assessments suggest Chinese sixth-generation development focuses on Pacific theater requirements, emphasizing long-range strike capabilities in carrier-based operations. This specialization could create regional advantages that complement rather than compete directly with Russian air superiority platforms. Russia's timeline advantage stems from strategic decisions made years earlier. The Advanced Research Foundation began sixth-generation research in 2014, while Western programs didn't receive serious funding until the late 2010s. This head start, combined with centralized development approaches, has created momentum that Western programs struggle to match. The implications extend beyond individual aircraft capabilities. Russia's approach integrates sixth-generation fighters into broader military networks, creating system-of-systems advantages that multiply combat effectiveness. These platforms coordinate with ground-based air defenses, satellite networks, and electronic warfare systems to create layered defensive umbrellas around strategic assets. NATO's response has evolved from skepticism to alarm as Russian capabilities become clearer. Alliance planners now acknowledge that air superiority assumptions underlying current military doctrine may become obsolete within the decade. Traditional approaches to power projection and conflict escalation require fundamental revision when facing adversaries with hypersonic, AI-enabled platforms. The economic dimensions are equally concerning for Western planners. Russia's component testing approach requires less upfront investment than developing entirely new aircraft, making sixth-generation capabilities accessible despite economic sanctions and reduced defense budgets. Western programs demand massive financial commitments that face political resistance in democratic societies. Production timelines reveal additional advantages for Russian approaches. While American F-35 programs have struggled with manufacturing bottlenecks and quality control issues, Russian incremental development reduces production risks. Modifying existing Su-57 manufacturing lines requires less infrastructure investment than establishing entirely new production facilities. The strategic implications reshape global power balances. Nations traditionally dependent on American air superiority guarantees face uncomfortable questions about future security arrangements. Russian sixth-generation capabilities could neutralize American forward deployment strategies that have maintained regional stability for decades. Middle Eastern and Asian allies are already exploring alternative security partnerships as confidence in American technological leadership wanes. Russia's successful integration of sixth-generation systems could accelerate these geopolitical shifts, creating new alliance structures that challenge Western influence. The arms race extends beyond national capabilities to include export markets. Countries seeking advanced fighter aircraft face limited options, with American platforms restricted by technology transfer concerns and Chinese systems lacking combat validation. Russian sixth-generation fighters could dominate international markets by offering capabilities unavailable elsewhere. Defense analysts warn that current Western approaches may prove inadequate for the challenges ahead. The combination of Russian technological advancement, Chinese production capacity, and Western bureaucratic constraints creates scenarios where democratic nations lose aerospace superiority for the first time since World War II. But behind the bold proclamations and secret tests lies a troubling reality that exposes the true state of Russia's fighter program. What are they hiding? Despite Russia's bold claims about the Su-57 fighter jet, the facts tell a different story. 14 years after its first flight in 2010, fewer than 40 Su-57s have been produced. That's a tiny number compared to China's J-20 fighters and America's F-35s, which have been built in the hundreds and thousands. The slow production pace points to deeper problems in Russia's aerospace industry, made worse by economic struggles and Western sanctions since the war in Ukraine began. Even though production was supposed to start earlier, it only began in 2019, almost a decade after the jet's first test flight. What's even more puzzling is that the Su-57 hasn't been used in combat. Instead of being deployed in Ukraine, where Russia could use its most advanced weapons, these jets have stayed within Russian borders, used only for air patrols. This raises serious doubts about whether the Su-57 is truly ready for battle. Western experts say there are major flaws that Russia isn't admitting to. The Su-57 doesn't seem to be as stealthy as advertised, and its radar signature is bigger than that of rival jets from the United States and China. In short, it may be more like a souped-up version of older jets than a cutting-edge stealth fighter. Another big issue is the engine. Instead of using a new fifth-generation engine, current Su-57s still rely on older engines from the Su-35, which limits their performance. The new engine is still in development, leaving a gap between what Russia is promising and what it can deliver. The export market isn't buying into the hype either. Russia has only just secured its first export deal, and even that buyer hasn't been officially named. Algeria is rumored to be the customer, but the secrecy and heavy discounts being offered suggest Russia is desperate to make a sale. Even India, one of Russia's closest defense partners, has expressed doubts. Indian officials have concerns about the jet's stealth and overall performance, showing that even longtime allies aren't convinced. Russia's messaging around the jet also doesn't add up. Officials claim to be testing sixth-generation technologies now, while also admitting that actual sixth-gen jets won't be ready until the late 2020s. This inconsistency suggests either false advertising or unrealistic timelines. Meanwhile, Russia's ability to build more jets is limited. The war in Ukraine has pulled resources away from aerospace projects, and sanctions have disrupted the supply of key parts. On top of that, quality control issues and technical problems have slowed down production even more. Russia's defense budget is also feeling the strain. With money and manpower going to the war, there's little left for large-scale aircraft development. What looks like a smart approach to testing new tech may be a way to cut costs. Perhaps the most embarrassing moment came recently when Ukraine reportedly hit a Russian airbase and damaged or destroyed a Su-57. That kind of vulnerability casts serious doubt on just how advanced and stealthy these jets are. All of this adds up to one thing. Russia's big talk about sixth-generation fighters looks more like smoke and mirrors than reality. Experts believe these claims are more about saving face on the global stage than showcasing real progress. And as long as Russia remains isolated and under pressure, its ability to keep up with global military tech seems increasingly unlikely. Despite the mounting evidence of problems and delays, one critical question remains unanswered. Is Russia's sixth-generation program a revolutionary breakthrough or an elaborate deception? The evidence presents a complex picture that defies simple conclusions. Russia has undeniably conducted extensive testing on Su-57 platforms, with over 700 documented flight hours validating new systems and capabilities. These aren't paper studies or computer simulations. Actual hardware has been flying and generating real performance data since 2023. The technological components appear genuine. Advanced electronic warfare systems, improved radar capabilities, and enhanced networking functions represent measurable improvements over existing platforms. Russian engineers have successfully integrated these systems into operational aircraft, demonstrating technical competence that Western analysts cannot dismiss entirely. However, the gap between component testing and operational deployment remains vast. Installing sixth-generation systems onto fifth-generation airframes doesn't create true sixth-generation fighters. The fundamental limitations of the Su-57 platform, questionable stealth characteristics, engine performance constraints, and manufacturing quality issues cannot be overcome through software upgrades alone. The timeline analysis reveals Russia's strategic predicament. American NGAD programs target deployment in the mid-20s, while European FCAS and GCAP initiatives aim for similar timeframes. China's Baidu program follows comparable development schedules. Russia's claims of operational sixth-generation capabilities by 2030 would represent a 5-year advantage over competitors, if genuine. This timeline advantage carries enormous strategic implications. 5 years of technological superiority could reshape global military balances, potentially neutralizing NATO's conventional advantages and forcing fundamental changes to alliance defense strategies. The stakes justify significant investment in deception operations if Russia cannot achieve genuine technological breakthroughs. The production numbers tell the most revealing story. Fewer than 40 Su-57s in 14 years of development cannot support claims of imminent sixth-generation deployment. Even if Russia achieves perfect integration of new technologies, manufacturing capacity constraints limit operational impact. Advanced capabilities distributed across small numbers of aircraft provide minimal strategic advantage. Financial pressures compound these limitations. Russia's defense budget faces competing demands from ongoing military operations, while international sanctions have disrupted supply chains for critical aerospace components. The component testing approach may represent cost-cutting measures rather than innovative development strategies, suggesting resource constraints rather than technological confidence. The export market response provides another crucial indicator. Despite aggressive marketing campaigns emphasizing sixth-generation capabilities, international buyers remain skeptical. Traditional Russian defense customers, including India and Algeria, have expressed reservations about Su-57 performance and reliability. This hesitation from established partners suggests underlying concerns about program credibility. Western intelligence assessments increasingly characterize Russian sixth-generation claims as strategic deception designed to maintain technological credibility despite mounting evidence of program difficulties. The gap between public assertions and observable reality suggests a military industry struggling to maintain relevance in an increasingly competitive global market. The geopolitical context supports deception theories. Russia faces growing international isolation, economic sanctions, and military pressure from multiple fronts. Maintaining the perception of technological competitiveness serves important strategic purposes, even if actual capabilities lag behind claims. The psychological impact of sixth-generation announcements may provide deterrent value regardless of operational reality. Yet dismissing Russian capabilities entirely would be premature. The Soviet Union achieved genuine technological breakthroughs despite economic constraints and international isolation. Russian aerospace engineers possess significant expertise and have demonstrated innovation throughout decades of aircraft development. The possibility of legitimate advances cannot be entirely discounted. The most likely scenario combines elements of both breakthrough and bluff. Russia has probably achieved genuine improvements in electronic warfare, networking, and artificial intelligence integration. These advances represent meaningful progress towards sixth-generation capabilities without constituting complete technological transformation. The final verdict may depend on factors beyond pure technology. Russia's willingness to accept risks that Western programs avoid, combined with centralized decision-making processes that enable rapid resource allocation, could produce operational capabilities that exceed paper specifications. However, sustained technological leadership requires industrial capacity and financial resources that current Russian circumstances cannot support. The truth likely lies somewhere between Russian claims and Western skepticism, significant but limited progress toward ambitious goals that remain years from full realization. Russia's seventh-generation fighter jet is reshaping the future of air combat. Packed with next-level technology, it is drawing concern from military powers around the globe. With stealth capabilities, advanced weaponry, and unmatched agility, the jet is changing the rules of engagement, forcing nations to rethink their defense strategies and preparedness for the battles of tomorrow. How does this cutting-edge aircraft threaten global air dominance? And what does its rise mean for the future of warfare? Join us as we explore the technology behind the game-changing jet and its potential to disrupt the balance of power in the world. The Su-57 is Russia's newest fighter jet. Built by Sukhoi, it has two engines and special features that make it hard to detect on radar. The Russian military started working on this plane in 1999 when they needed something more practical than their earlier design. While Sukhoi calls it the T-50 internally, it's better known as the Su-57. It is a big step forward for Russia, as it is their first military plane built to avoid detection, and they plan to use its design as a blueprint for more stealth aircraft in the future. The Su-57 can do many jobs in one plane. It can fight other aircraft in the air, hit targets on the ground, and attack ships at sea. The plane is hard to spot on radar, can turn quickly in tight spaces, and flies fast without using extra fuel. Its computers all work together, and it can carry lots of weapons. The first test plane took to the sky in 2010. However, getting the design right proved challenging. The team ran into problems with how the plane was built and how its systems worked during testing. Things got worse when the very first plane meant for actual military use crashed before it could even be handed over. In 1979, the Soviets knew they needed better fighter jets ready to fly by the 1990s. They picked Mikoyan to handle this project, and the company started working on the MiG 1.44. Sukhoi was not chosen for this project, but they did not let that stop them. In 1983, they began their research to create cutting-edge fighter technology. This work led to their test plane, the S-32, which they later called the S-37 and finally the Su-47. What made this plane special was how its wings pointed forward instead of backward. When the Soviet Union fell apart, money dried up. This meant the MiG 1.44 project kept getting pushed back. The plane didn't take its first flight until the year 2000, 9 years later than planned. The costs were just too high, so they had to cancel both the MFI and LFI projects. Despite the setbacks, Russia still wanted new fighter jets, and in 1999, the Russian Ministry of Defense started fresh with something called the PAKFA or I-21 program. Because they were struggling with money, they had to be smart about their next fighter jet. Instead of making two different planes to replace the Su-27 and MiG-29, they decided to build one plane that could do both jobs. To keep costs down, they planned to make it smaller than their previous test jets. The new plane would be bigger than a MiG-29, but smaller than a Su-27. It would also be much lighter. The old MiG test plane weighed 28.6 tons, 63,000 pounds, and the Su-47 weighed 26.8 tons, 59,000 pounds. The new design would weigh a lot less than either of those. Sukhoi and Mikoyan had very different ideas about how to handle this big fighter jet project. Mikoyan wanted all three design teams, themselves, Sukhoi, and Yakovlev, to work together as partners. The team with the best design would take the lead. But Sukhoi came with their plan. They wanted to be in charge from day one. They had already figured out who would build the engines, who would make the electronics, and which research labs would help out. Their proposal covered the whole process from start to finish. The two companies also had different ideas about what kind of plane to build. Mikoyan wanted to make a smaller, less expensive jet. Their E-721 would weigh between 16 and 17 tons, which is about 35,000 to 37,000 pounds. It would use two Klimov VK-10M engines, each producing between 10 and 11 tons of thrust. Sukhoi went the opposite way. Their T-50 would be bigger and more powerful, weighing between 22 and 23 tons. They planned to use two Lyulka Saturn AL-41F1 engines, each producing about 14.5 tons of thrust. In April 2002, Russia's Ministry of Defense picked Sukhoi over Mikoyan to lead the new fighter jet project. This wasn't just because of their good design. Sukhoi had proven themselves in the 1990s by successfully making different versions of their Su-27 jet and selling them to other countries. This success meant they had enough money to handle such a big project. The head of the Russian Air Force, Vladimir Mikhailov, said they planned to start test flights in 2007. Meanwhile, Mikoyan didn't give up. They kept working on their own smaller jet, the E-721, which they called the LMFS, meaning Light Multifunctional Frontline Aircraft in Russian, but had to pay for it themselves. When designing the Su-57, Sukhoi looked closely at America's F-22 stealth fighter. They liked some things about it, but wanted to fix what they saw as problems. The F-22 couldn't use its moving engine nozzles to help it roll side to side or turn left and right. It also didn't have much room between its engines to store weapons. And if its engine controls stopped working during extreme maneuvers, it would be hard to recover. Sukhoi didn't think the F-22 could carry enough weapons, especially since it mostly focused on air-to-air missiles. They needed their new jet to do more than that, and they designed it to fix all the problems they had envisioned. The Su-57 has a wide, smooth body that blends into its wings. Two engines sit far apart from each other. Both the tail fins and horizontal stabilizers at the back can move fully, and the tail fins angle outward to help hide from radar. The wings are shaped like triangles and have different moving parts along their edges to help control the plane. The engine's nozzles can point in different directions, giving the pilot more control. The plane has special extensions where the wings meet the body. These push the plane's balance point forward, making it less stable but more agile. These extensions have moving parts that help control airflow and keep the plane steady even if the engine controls stop working. To slow down in the air, the plane's wing parts move up and down, while the tail fins turn inward to catch more air. While most of the plane is made from metal, and it also uses a lot of composite materials. These make up about 22 to 26% of the plane's structure and cover about 70% of its outer skin. The designers had big plans for the Su-57 from the start. They wanted it to carry lots of weapons inside the plane instead of hanging them underneath. Between its two engines, there's a large space with two main weapon bays, one behind the other. There are also smaller bays near where the wings join the body, with special triangle-shaped covers. Keeping weapons inside helps the plane in two ways. It stays stealthy because nothing is sticking out to see on the radar, and it can fly better because nothing is creating extra drag. The Su-57 can move with incredible control in any direction, thanks to three main features: its naturally unstable design, which helps with control, its advanced KSU-50 flight control computer, and its angled engine nozzles that can point the thrust. These features let pilots safely perform extreme maneuvers, like the Pugachev's Cobra, where the nose points straight up while flying forward, or the Bell maneuver where the plane seems to hang in the air. The plane can even rotate in place without losing much height. The way it's built, along with its powerful engines, lets it reach twice the speed of sound. It can even fly faster than sound without using its afterburners, cruising at 1.3 times the speed of sound. This gives it a big advantage. Its weapons can reach farther than older fighters' weapons could. With its large fuel tanks, the Su-57 can fly at supersonic speeds for more than 930 miles, which is over twice as far as the older Su-27 could go. If pilots need to fly even farther, they can extend a probe to refuel in the air. The Su-57 is the first Russian military plane built to hide from radar. Think of it like hiding from a flashlight beam. The plane uses several tricks to avoid being seen. Just like the F-22, its edges are lined up in a way that makes radar bounce away instead of back to the source. The edges of the wings and control surfaces are set at careful angles, and even the skin panels have jagged edges, all to scatter radar signals in different directions. Instead of hanging weapons on the outside where radar can spot them, the plane keeps them tucked away inside. The antennas sit below the surface of the skin rather than sticking out. The plane's surface is also covered with special materials that soak up radar waves like a sponge, making it harder for radar to get a clear picture of the aircraft. When the plane's heat-seeking sensor isn't being used, it faces backward, and its backside is coated with radar-absorbing material. The engines could show up clearly on radar, like a bright spot, so the designers had to get creative. They lined the air intake tunnels with special radar-absorbing coating and made them curve like a snake. This helps hide the front parts of the engines. For the parts people can still see, they put a slanted metal grid in front, placed about 0.7 to 1.2 times the width of the tunnel away from the engine. It's the same trick used on the Boeing FA-18EF to make the engines harder to spot on radar. The whole plane is built with much tighter measurements than older Russian fighters. Think of it like building with Lego blocks. The pieces need to fit together perfectly with no gaps to keep the plane hidden from radar. By combining its special shape and radar-absorbing coating, the Su-57 is 30 times harder to spot on radar than the older Su-27. The Su-57 uses two special engines called AL-41F1s. Think of them as super-powered versions of older Russian jet engines. When running normally, each engine can push with a force of 9 tons. These engines have a smart computer brain that controls them automatically. It's connected to the plane's flight controls, which helps the pilot steer and handle the aircraft more easily. The engines also have some clever features to help them work better. When the plane flies very fast, special ramps in the air intake adjust to help the engines breathe better. There are also metal screens that can slide into place to stop rocks or debris from getting sucked into the engines. This is helpful when the plane needs to take off from rough airfields. But these engines have had some problems. Back in 2011, at an air show in Moscow, one of the planes had to stop taking off because its engine started having trouble. Later in 2014, the Indian Air Force said they were worried about how well these engines worked and how reliable they were. Russia is developing an improved Su-57 fighter jet. In the mid-20s, they plan to equip it with new AL-51F1 engines. These engines will be much more powerful, with 11 tons of thrust normally and 17 tons with afterburners. They'll also be more reliable, efficient, and cost less to maintain. To avoid detection, the engines will have a lower radar cross-section and give off less heat. Special materials in the front section and jagged exhaust nozzles help reduce their radar signature even further. So in a few years, the Su-57 should be stealthier, more powerful, and more dependable thanks to its cutting-edge engines. A big step up for Russia's most advanced fighter. In 2023, the engine makers started working on something different, a flat exhaust nozzle instead of the usual round one. They started testing it in late 2024. Since they had to make this new nozzle fit the existing plane, they designed it carefully so they wouldn't have to make big changes to the rest of the aircraft. Inside the Su-57's body, there are 4 hidden spaces to carry weapons. The 2 main spaces run down the middle of the plane, each about 4.4 meters long and 0.9 meters wide. 2 smaller triangle-shaped spaces sit on the sides, tucked under where the wings meet the body. To launch these weapons, the plane uses special racks made by a company called Vimpel. The main compartments have 2 kinds. One type can handle weapons up to 300 kilograms, while the stronger type can handle heavier weapons up to 700 kilograms. The side compartments use a different kind of rack to hold their weapons. The plane has room for 6 missiles to shoot down other aircraft. 4 bigger ones fit in the main weapon bays in the middle of the plane, while 2 smaller ones tuck into the side bays. For fighting other planes at medium distances, it uses the KR-77M missile. This is a better version of an older missile, with new features like a smarter radar seeker in the front and an improved motor that fires twice. For close-up fights, it uses the R-74M2 missile, which follows the heat from other aircraft. They made this missile skinnier so it could fit inside the plane's weapon bays. They are also working on a completely new short-range missile called the KMD to replace it someday. When the plane needs to hit targets far away, it can use an even bigger missile called the Izdeliye 810. This is an upgraded version of another missile, made shorter so it fits better inside the plane. The plane can carry 2 of these in each main weapons bay. If needed, it can also hang the older version of this missile on the outside of the plane. The pilot looks at 2 big screens that are 38 centimeters across and about the size of a laptop screen. These screens show all the important information, just like in the Su-35S. There's also a smaller screen and a control panel with buttons. Instead of old-style dials and gauges, everything is digital. Up at eye level, there is a display that projects flight information onto a clear screen, so the pilot doesn't have to look down. It shows a view that's 30 degrees wide and 22 degrees tall. To fly the plane, the pilot uses a joystick and 2 throttle levers. All the main controls are right there on these 2 handles. The pilot can control most things without moving their hands away. The clear cover over the cockpit comes in 2 pieces. The back piece slides forward to close up. This cover has a special metal coating on it to help hide the plane from radar. The plane uses a Russian-made computer system to run everything, based on a chip called the 1890 VM8YA. One of the key goals for the Su-57 is to get all its electronics working together seamlessly. The fancy term for this is sensor fusion. When everything talks to each other, it makes the pilot's job a whole lot easier. They can see the full picture without having to juggle a bunch of different info. The plane's computer brain is called the Information Management System. It's the thing that keeps all the other systems in sync. The 2 big ones are the Sh-121 radio system and the 101KS atoll cameras and sensors. Sukhoi is handling the electronics integration in-house, which is a big job. The software has over 4 million lines of code. They're using fiber optic cables to keep everything connected. Russia's defense ministry shared some big news on Christmas Day 2020. They said the Su-57 had officially joined the Air Force. The first production planes were sent to a base in Lipetsk, in the southern military district. These initial jets will be used to figure out tactics, train crews, and put the Su-57 through its paces. They want to see how it performs day to day. The first unit set to fly the Su-57 full-time is the 23rd Guards Fighter Aviation Regiment. They are based out east, right next door to the factory. In May 2022, a couple of months into Russia's invasion of Ukraine, some Russian sources said they had sent Su-57s into the fight. The claim was that these stealth jets fired missiles at Ukrainian targets from long range, keeping well clear of Ukraine's air defenses. Then in June, the RIA Novosti news agency reported that 4 Su-57s had teamed up over Ukraine to hunt down and wipe out Ukrainian air defense systems. The Russians said this network of stealth fighters showed off the Su-57's radar-dodging tricks in a real combat situation. So if these reports are accurate, Russia's cutting-edge Su-57s have gotten a taste of combat in Ukraine. But just like the rest of the Russian Air Force, they're having to play it safe and keep their distance to avoid Ukraine's surprisingly tough air defenses. The Su-57 fighter jet is packed with cutting-edge tech that will make pilots' lives easier and help it sneak past enemy radars. The Russians are betting big on this plane, hoping it will give their Air Force a serious boost in the coming years. Modern warfare has always centered around two things: intelligence and aerial superiority. While unmanned combat aerial vehicles like the Boeing MQ-28 and Ghostbat Kratos XQ-58 Valkyrie have been the talk of recent aerial warfare technology, cutting-edge war helicopter designs have forced their way into the conversation, with Russia's recent $3 billion invention taking center stage. How does this invention shape the future of aerial combat? What makes this helicopter different from its predecessors? Let us unpack the significance of this aerial combat vehicle as Russia tests its $3 billion helicopter. The superpower countries of the world have always been at war over economic and territorial disputes, leading to the continuous destruction of lives and properties. While alliances and opinions change over the years, redirecting the brutality across the continents like a war version of whack-a-mole, one thing remains constant: inventions. War has always found a way to precipitate some of the greatest technologies in the world, especially combat vehicles on land and aerially. However, the tide has changed, and modern combat has gone well beyond force, with stealth coming into play, leading to the construction of cutting-edge aerial technologies like the Kratos XQ-58 Valkyrie, the Dassault Neuron, and the Chinese CH-7. While these warjets have gained some popularity and wide acclaim for their effectiveness in wartime, helicopters have been neglected in the grand scheme of things. The history of helicopters is dated back to the Second World War with the creation of the Fokker-Achilles Fa-223 Drache by Nazi Germany. The Fokker-Achilles Fa-223 had a single 750-kilowatt Brahmo 323 radial engine used to power two 3-bladed, 39-foot rotors mounted on twin booms on either side of the 40-foot cylindrical fuselage. The design created a wing-shaped effect, shaping up like some mechanical bird. At a top speed of 180 kilometers per hour, the Fa-223 could cruise at 175 kilometers per hour and climb to an altitude of 7,100 meters. At the time, it seemed that they had built the world's eighth wonder, as no one else had ever seen or built any such thing as a helicopter. Of course, there were biplanes like the 1935 He-49, which was primarily designed for stealth purposes. However, the invention of the Fa-223 brought about a new type of reality and changes to aerial warfare. The Nazi German army was quite impressed with the first experimental helicopter, the Focke-Wulf FW-61. However, it was not a military helicopter. It was only an experimental creation of Focke's brainchild. However, the Nazi Germany defense did not mind his avant-garde approach. They needed an aerial combat vehicle that could carry 700 kilograms of payload without a problem, leading to the creation of the Fa-223 prototypes. A fun fact about the Fa-223 is that it used to be called the Fa-226, with no specific reason given for the redesignation of the name. Owing to its status as the first of its kind, it needed to go through flight testing. First, it was taken through a tethered flight test, and then an untethered flight test on August 3, 1940. While the Fa-223 seemed to have been credited with being the very first helicopter ever made, it was halted in production by the Allied bombing that hit Nazi Germany in June 1942, when Delmenhorst, their factory base, was incessantly bombed to the high heavens during the Second World War. Hence, the production phase was hampered, and only 20 were built. Although the Fa-223 maintained its position as the first military helicopter ever built, the Sikorsky H-5 took the spotlight. While the Fa-223 was mainly designed for military use, The Sikorsky H-5 ensured the creation of a chopper that could be used by the military and also purchased by civilians. The H-5 was originally developed by Sikorsky as an S-48. However, the United States Air Force redesignated it as an R-5. The helicopter was designed to carry out certain functions, including increased payload, endurance, speed, and service ceiling, compared to its predecessor, the Sikorsky R-4. The Sikorsky H-5 was a different beast. It differed from nearly every other chopper to have ever been made. It has a beastly rotor diameter and a longer fuselage than its predecessor, the R-4. However, as Sikorsky's market grew, making a name for itself in the military airspace, a bit of capitalism set in. Hence, they decided to modify it into a version more civilian-friendly. Setting up a capitalist venture isn't too difficult to create, especially in a class-based society where the proletariat would pay over the odds to seem completely out of everyone else's league. To lean into the capitalist market, the Sikorsky S-51 was designed with a greater rotor diameter, greater carrying capacity, and an evenly shared gross weight, providing carrying capacity for 3 passengers plus the pilot. The S-51 was designed to appeal to civilians, but also to be used on military and Air Force bases. However, it became the first helicopter to be sold to a commercial user. While the military understood the difference between the commercial usage of the flight, 11 S-51s were still ordered by the United States Air Force. Also, they were redesignated as the R-5F, and 92 of them were sent to the Navy as the HO-3S1, commonly referred to as the Horse. The Navy ordered 4 S-51s from Sikorsky in late 1946 and used them during Operation High Jump. However, the S-51s were placed into the inventory as HO-3S1. It was stealthily ferried across the seas using the seaplane tender USS Pine Island, or AV-12, as popularly called. The helicopter, first flown by Lieutenant Commander Walter M. Sessoms, became the first ever helicopter flight across the Antarctic. However, as time went on, warfare evolved, requiring an improvement in the invention of helicopters. While the S-51 had enough modifications to be both a commercial and military plane, it had more military ramifications. During Operation High Jump, it was used as a utility helicopter for rescue and mercy missions throughout the world, highlighting questions if it should have been allowed for commercial use in the first place. While the United States dominated the helicopter space with Lockheed Martin and Sikorsky, a global arms race loomed in the air like a dark cloud, and the world's superpowers followed suit, especially the United States' biggest counterpart, Russia. While early helicopter development has been through different phases of creation and versions, Igor Sikorsky remains one of the most important shapers of the modern helicopter industry. However, as his name might suggest, he was never American. He is a Russian man who fled the country during the Bolshevik Revolution, seeking new opportunities in the United States. And just like that, the Russians lost a super inventor to the United States, owing to an instability in their government. Although Russia lost Igor to the United States, they weren't fazed by the success of his invention, as they believed that they could do the same. Hence, while Igor built his choppers in the United States, Russia reacted with a chopper of their own, the Mi-1. This is Russia's first helicopter to ever make it into mass production, developed by Mikhail Mil. Before 1930, Mikhail Mil had been working on a winged aircraft that used rotation to propel its locomotion. However, a good dream is determined by planning. Mil put a lot of work and planning into the design, but he kept failing until 1946. His first designation was the EG-1, after becoming the head of the OKB-4 Design Bureau in Toshino, Russia. While he created his helicopter and failed many times, he finally figured it out. He created a final design called the GM-1, translated as Helicopter Mila, or Mil's helicopter in English. While the Sikorsky version tried to entertain more strength, dexterity, and complex rotor movement, the Soviet engineers opted for more simplicity, increasing efficiency in helicopter control, unlike the American choppers. To achieve this efficiency, they made a rotor hub with spaced vertical and horizontal hinges. The first prototype completed its first untethered flight on the 20th of September, 1948, piloted by Mikhail Babalov. While the test was a success, the Russian military demanded an official state trial, so Mikhail agreed to their demands, and they launched their trial in 1949. During testing, 2 prototypes of the helicopter were crashed. However, Mikhail did not give up. He put in a bit more work than usual, made a few tweaks, and found an answer to the reasons for the crash. The success of his work not only gave him worldwide plaudits, but the Russian military placed a demand for his chopper, albeit under a new designation called the Mi-1 for Mil initials. While the production was initially limited to a series of only 15, ordered on the 21st of February, 1950 in Factory Number 3 in Moscow, production was not increased until 1951, when Joseph Stalin witnessed the helicopter in action and deemed it important to their warfare. The 1950s saw the growth of rotor technology, hence the Mi-1s were redesigned for increased reliability, especially the number of hours it could spend in flight. First, they created the Mi-1T, with the T representing Treksochasovoi, translating to 300 hours in English. Then rotor capacity improved even further over the year, with another 300-hour improvement in the Mi-1A, and then to 1,300 by the end of production. While the Mi-1s were initially built for carrying cargo and capability to play bit parts in stealth, they figured that they could do more with a different variant that could carry even heavier payloads and operational equipment, including full radio and bind flying instruments, and utilized a more reliable engine, the AI-26VF, hence the release of the Mi-1T than the Mi-1A. However, as technology improved, the Russian defense was no slouch either. The early 60s saw the introduction of enlarged cabins and engines even more powerful and reliable than the AI-26VF, which allowed the accommodation of 3 passengers on a bench behind the pilot. Russia at the time anticipated war, and they wanted every air superiority that they could possibly have over their adversaries. So they opted for the production of a rather distinct version of the Mi-1s at the time, designating it the Mi-1Mu. The Mi-1Mu was specifically designed as an anti-tank helicopter. The rationale behind it wasn't too difficult to understand. Talking about defenses against a chopper, an armored tank, and surface-to-air missiles could definitely do the job. Hence, in 1961, when Russia looked casually for a counter against tanks and surface-to-air missiles, they created the first Soviet attack helicopter. While reports suggest that they had a really good trial run, for some reason, it wasn't accepted into the production stage. The trading rumor at the time was that it had a small payload capacity, and that just wouldn't do the trick for the Soviet Army. Although the Russians had responded positively to the United States helicopter production with some of their own, they were in for another rude awakening when America released a completely different beast of a helicopter in 1962, the Bell AH-1 Cobra. The Cobra was created in response to the United States Army's request for an interim gunship during the Vietnam War, and it used the transmission and rotor system of the Bell UH-1 Iroquois, which had already proven itself to be a capable platform during the conflict, but paired it with a redesigned narrow fuselage among other features. It was the perfect combat helicopter. It was equipped with stub wings used to anchor various weapons, a chin-mounted gun turret, and an armored tandem cockpit, meaning the pilots were seated one behind the other. It was shaped in a very slender figure for agility, almost reminiscent of a Cobra. Also, the slim shape makes it difficult and, in some cases, nearly impossible to get hit by tanks or surface-to-air missiles, except there is some form of pinpoint accuracy to hit the chopper. Its first appearance came through during the Vietnam War, in June 1967 to be precise. It provided fire support to friendly ground forces. In some sort of ways, it was like calling in the cavalry. Its effectiveness was almost dreamy, as no one really knew how capable it could be. Often it was paired with the Hughes OH-6 Cayuse, a single-engine light helicopter designed and produced by the American aerospace company Hughes Helicopters. While the Cayuse performed its stealth and scout mission, gathering intelligence, the Cobra followed closely like a guard dog, shooting to eliminate any form of threat in its way. The tag team operation was referred to as the Hunter-Killer mission. The Cayuse played the hunter, and the Cobra played the killer. The Cobra became the talk of aerial warfare all over the world, with an unprecedented effect on aerial combat. While one might think of the United States hoping to hoard such military might, surprisingly, they were ready to sell. And nations such as Israel, Turkey, and Japan reached out to buy, increasing their military might with the United States' cutting-edge technology. While warjets keep getting accolades for their service in war, as in good reasons, the Cobra AH-1 also became a fundamental part of some of the greatest wars ever fought in the name of the United States. Aside from the Vietnam War, the Cobra dealt devastating blows in Vietnam, Grenada, Panama, and the Gulf War. However, as time went on, scientific evolution caught up with the Cobra, leading to the creation of its replacement, the Boeing AH-64 Apache, during the 1990s. Although the Cobra might have been a United States creation, it was also used prolifically by the Israeli Air Force, who used it for combat during the Lebanon War of 1972, giving them an edge in the war. Upgraded versions of the Cobra have been developed, such as the twin-engined AH-1C Cobra, otherwise called the Super Cobra, and the experimental Bell 309 King Cobra. Although the Cobra seemed like the peak of modern combat helicopters at its inception, it eventually became surplus to requirements and has been reused for other purposes, including civilian ones. Numerous examples have been converted to perform aerial firefighting operations. A perfect example is the United States Firewatch Services, which acquired Cobras that have been used in combats during the Vietnam Wars and retrofitted them into a red-white perfection with infrared sensors, so they can be used to gather close-in intelligence from ground troops fighting fire. While the world watched the slim Cobra showing off at war and eventually retiring as a firefighter outfit, other world superpowers looked to create a better version of this combat monster. While some have tried and failed at the production level, Russia has come up with a $3 billion helicopter project that has left the military combat landscape in awe. The Russian military had always had a trusted template for their helicopters, Mikhail Mills. After his discovery in the 40s through the cities, the Russian military fell right in league with world superpower countries that possessed a combat helicopter. However, while that time may have well passed, the Mi-17, introduced in 1975 as the Mi-M8, resumed production in 2024 at factories in the Kuzan and Ulan-Ude. While some might have an idea of this chopper's capabilities, it has been stepped up to a whole new level, and no one saw it coming. Of course, it isn't news that Russia remains at war with Ukraine. It would seem another time of war has created another cutting-edge technology in aerial warfare, a recurring theme in the history of warfare. The original version of this chopper was built from the basic Mi-8 frame, fitted with larger Klimov TB3 engines, rotors, and transmission, along with fuselage improvements for extra heavy load capacity. While most choppers struggle with hot and high conditions, where there is a low air density due to high ambient temperature and high airport elevation, and air density decreases with increasing temperature and altitude, Russia's new $3 billion Mi-17 is equipped with optimal engines like the 1,545 kilowatt Isotov TV3117VM to battle these conditions easily. Although Russia has a reputation for keeping its military intelligence a secret and unleashing it unexpectedly in combats, it has decided to export the Mi-17s, flexing its newfound military might and them sending a message of caution and protection. The helicopter has a specific design that has kept it completely different from every other kind. Its recognizable trademark is the tail rotor added to the port side instead of the conventional starboard side and dust shields in front of the engine intakes. The production sent a shockwave down the spines of competitors around the world, not only sparking a global arms race, but buyers queuing at Russia's door, banging on for a chance to buy this super air beast. In March 2001, Russia eventually gave China a license for production, albeit led by Mil Moscow Helicopter Plant JSC and the Sichuan Lantian Helicopter Company, limited in Chengdu, Sichuan Province, as a joint venture. Fast forward to the 21st century, and countries like Argentina, Bangladesh, and Peru have come as clients looking to buy this helicopter in an arms deal worth millions of dollars to Russia. While the military and economic tussle between Russia and the United States remains a reference point, it has never stopped them from doing business even in arms, where both countries appear to be the leading light. Their first buy from the Russian military came in 2009, and they handed over 4 of the cargo helicopters to the Pakistan Army to facilitate its counterterrorism operations, while they played Big Brother in their diplomatic relations with Pakistan. However, not only has the United States used this Russian state-of-the-art helicopter for diplomatic reasons, they have also reportedly considered adding it to their special forces ranks, using it to obscure troops' movements. Fast forward to 2022, the Joe Biden administration announced that the United States would be supplying Ukraine with 11 Mi-17s to aid them in their defense against Russia. Imagine a capitulation of Russia under its own $3 billion cutting-edge technology. Over the years, warfare has evolved to reach a new peak, transitioning from land to naval and aerial combat. Consequently, there has been continuous development of new weapon systems capable of fighting in modern warfare. While the United States has been constantly recognized as the leading country in terms of hypersonic jet engine development, Russia has come into the fray now, introducing its billion-dollar fighter jet engine to dominate the skies. How important is the invention of this aerial marvel? Can other countries compete with this new cutting-edge invention? Join us as we discuss Russia's billion-dollar fighter jet engine in action. The global balance of power has always swung like a pendulum, tilting toward the nations with the highest economic and military power. Over the years, military power has significantly shifted from Europe to North America and vice versa. However, more recently, the United States seems to have taken the lead, progressing its economy and producing weapons of mass destruction, ranging from bunker busters to propellers and supersonic jet engines. In the 21st century, warfare seems to have evolved past the shackles of Mach 1 to Mach 3 speed fighter jets, with top nations' eyes set on reaching Mach 6, making them nigh unstoppable in the skies. Imagine a fighter jet capable of stealth and reaching a speed of almost 6,000 kilometers per hour, countering every type of anti-aircraft defense in the world, with little to no trouble at all, a real game changer. However, this technology has been theorized much more easily than actualized. While the concept has been the top country's brainchild, creating a technology of that magnitude requires a lot more than geniuses and willpower, with funding right at the center of it. But what really makes hypersonic technology just so important that every top country is scrambling for a chance at it? Hypersonic technology definitely changes the game at every level, whether in war or just in commercial day-to-day traveling. For example, countries like the United States and China have been locked in a race to create the first operational fighter jet. While China has had its bit-part failures and successes, they have not really been able to come up with an operational hypersonic jet engine that can be utilized during war or even for commercial flights. On the flip side, the United States has recently turned a corner and finally come up with an experimental hypersonic jet in the SR-72, son of Blackbird, while also having the Defense Advanced Research Project Agency, often called DARPA, on their side, working in tandem to make the project get even strong enough to use in warfare. While the United States takes a huge leap forward in developing this monstrous aerial technology, China has continued with their flight tests, hoping to be the first Indo-Pacific country to create competition for America's lead. However, while the United States remains in the lead and China follows aggressively behind, the world seems to overlook Europe. Russia, meanwhile, has brought the world's attention back with the near completion of its billion-dollar hypersonic fighter jet engine project, completely changing the game and taking the lead. But why was Russia initially overlooked? Ever since the annexation of Crimea in 2014, Russia seemed to have consistently attracted more enemies than friends, especially in the West, in the Indo-Pacific regions, where it believed that the Kremlin's annexation of Ukraine was simply born out of a greed to take over the world, bringing back the glory days of the disbanded Soviet Union of the 1990s. Fast forward to the 21st century, and the Kremlin has faced economic and financial restrictions, primarily imposed by the United States and supported by other countries, which the Kremlin believes are inspired by the defiant United States. Hence, no one thought that a country fighting a war and suffering restrictions on its economy from most of the global market controllers would have the resources and willpower to not only fund the creation of a hypersonic jet, but also be on the verge of making it operational. Is history really about to be made? While reports suggest that they are nearly there, just how much does their creation compare to the SR-72 son of Blackbird? While nuclear war was the order of the day back in the mid-40s, aviation now is at the center. Over the years, philosophers and other specialists in war have theorized just how important gaining air superiority is to creating a massive advantage during a war. Like Omar Nelson Bradley once said, air power has become predominant, both as a deterrent to war and in the eventuality of war, as the devastating force to destroy an enemy's potential and fatally undermine his will to wage war. It would seem that the United States and Russia especially took that to heart with their heated arms race in creating the fastest fighter jet in the world. The SR-72 son of Blackbird was created and intended for performing the most essential functions of a military aircraft, including intelligence, surveillance, and reconnaissance missions. Although the idea seemed original and almost nigh impossible, it didn't come from a vacuum. Rather, it stemmed from the evolution of warfare, including the introduction of anti-access, aerial denial tactics that have become the go-to strategy for opposition countries with limited aerial firepower. Hence, Justin Bronx, a senior research fellow in air power and technology at the Royal United Services Institute, otherwise called RUSI, argued that the rise of the anti-access or aerial denial tactics is a wake-up call for the military to adopt speed more than stealth to negate the risk of getting their aircraft shot out of the sky by surface-to-air missiles after being detected on radar. His advice, paired with a recurrent shooting down of American aircraft in enemy airspaces, prompted the emergence of the SR-72 son of Blackbird in 2007, when the Skunk Works department of the Lockheed Martin Advanced Development Programs. The United States Air Force had finally decided to retire the SR-71, hence the idea for a prototype that would be at least 2 times faster than the retired SR-71 Blackbird. In 2006, the Skunk Works division started working with Aerojet Rocketdyne, a subsidiary of American defense company L3Harris that manufactures rocket, hypersonic, and electric propulsive systems for space, defense, civil, and commercial applications. The company was tasked with creating an engine capable of transitioning from 0 to Mach 6 speed, generating enough kinetic force to help an aircraft travel at 6,400 miles per hour, hence the deliberation on engine choice. After much thought, Lockheed reached an agreement with Aerojet Rocketdyne to combine their scramjet engine, a supersonic combustion ramjet, with their turbojet engine. Hence, the engine was referred to as a turbine-based combined cycle. The SR-72 son of Blackbird was always envisioned to have an air-breathing propulsion system, meaning that the engine will rely on using the oxygen from the surrounding air to burn fuel, generating thrust and propelling forward between speeds of Mach 1 and 6. Unlike the rocket engines that carry their liquid oxidizer to burn fuel and propel the aircraft, the son of Blackbird was going to be completely different, as the air-breathing propulsion system would be supporting operation at subsonic, transonic, supersonic, and hypersonic speeds. But just how did they plan to create a jet that could go from the lowest speed anyone can imagine to hypersonic speed? And how will the engines work? The turbojet engines can naturally function from a resting point or 0 to at least Mach 2.2, which is the standard speed in commercial jets and some military jets. The turbojet engine is perfect for takeoff, acceleration, and cruising at subsonic or low supersonic levels, giving it relatively frightening speed. However, the United States Air Force had a much stronger requirement, which could only be met by combining the turbojet with the scramjet. The scramjet engines remain in position and docile until the aircraft is moving. When it accelerates to over Mach 2.5, using the turbojet engine, the scramjet takes over and accelerates up to Mach 6, depending on how fast the pilot wishes to go. But just how are these engines combined during flight? Lockheed Martin came up with a genius aerodynamic system where the engines are joined together with the same inlet and nozzle with which they take in air, and then a valve redirects the airflow from the turbojet engine into the scramjet engine when the aircraft is traveling beyond Mach 2.5. This completely changed the game for the United States, establishing them as the top dog in aerial warfare. However, questions remain about the importance of having a combined turbojet and scramjet engine to cater towards achieving Mach 6 speed and beyond. Well, the reason for that is that there isn't an engine in the world capable of going from 0 to Mach 6 without stalling or risking a genuine explosion of the whole aircraft. Hence the emergence of this complex engineering. It's like a James Bond movie where a car turns into a boat, then a ship becomes a submarine, all while sharing the same hull. But this time, think about it in aircraft. More importantly, the two engines in question can only work at a certain velocity. For some context, the turbojet engine will stall and explode should it be forced to take on more than an average speed of Mach 2 to Mach 2.2, while the scramjet doesn't even work at all until the aircraft is moving in full flow and hits Mach 4. The United States Air Force noted that having a hypersonic jet will definitely shorten an adversary's reaction time to operations. Imagine an aircraft that could travel at 6 times the speed of sound, going behind enemy airspace for stealth or reconnaissance missions, and maybe even strike if authorized and going back to base before the enemy realizes what has hit them. While the aircraft engine remains in construction, questions linger over what kind of material and hardware would be needed by the aircraft to handle such speed. Aircraft travel has always had to do with energy and friction. The atmosphere definitely contains air. Therefore, when an aircraft travels through the atmosphere, it pushes the air consistently, displacing a massive volume of it, eventually generating a lot of friction, which then creates heat buildup. However, there are metals capable of handling travel at Mach 2.2, but at Mach 6, there is an increased speed, so the air is being pushed back more, generating more friction in the process, and enough heat to nearly set the aircraft ablaze. Hence, as important as it is to get an engine that could possibly transition from turbojet to scramjet to kickstart it at Mach 4, getting the required materials to build an aircraft that could manage such speed without being set on fire before completing a trip and returning to base was just as important. It's like taking a ride on a bike. Imagine traveling at low speed at first. The rider feels a gush of air pushing back gently against their face, but as soon as they accelerate, the air moves back faster and it gets more intense and just a little hotter than it used to be. Now imagine that with aircraft traveling at a hypersonic speed. Not only does it create drag, but it also heats the metal and in some cases might ignite it. It is mainly referred to as aerodynamic heating. At speeds of Mach 6 and above, aerodynamic heating generates temperatures sufficient to melt conventional metallic airframes, prompting engineers to consider making critical components from composites, such as high-performance carbon, ceramic, and metal mixes used in intercontinental ballistic missiles and the retired space shuttle. Although the mixed component solution has been discussed extensively, the aerodynamic heating problem remains. However, reports have consistently suggested that the first prototype will eventually be released by the Lockheed Martin company and will possibly be equipped with the technology to launch hypersonic missiles. While the world anticipates its eventual release, some of the superpowers, especially China and Russia, are now in a race against time to create their own engines in a bid to rival the United States' SR-72 son of Blackbird. Although the United States has pushed the envelope further than nearly anyone while experimenting with different ways to increase aerial dominance, Russia has pushed back with the development of the Izdeliya-30. The Izdeliya-30 is an afterburning low-bypass turbofan engine being developed by NPO Saturn to succeed the Saturn AL-41F1 for improved results in their fighter jet, Sukhoi 57. While the United States remains in a limbo on the possibility of reaching the production stage with the turbine-based combined cycle as their only hope but struggles to push the envelope from the turbojet engines, Mach 2.2 max, to jump immediately to Mach 4 and activate the scramjet, Russia decided not to push the envelope too far. Instead, they created an advanced variable cycle turbofan engine with thrust vectoring capability that could foster supercruise, meaning that it helps the aircraft sustain a level of supersonic speed without turning on the afterburners, reducing the thermal signature, and consequently making it nigh impossible to detect on the opposition's radar. Although the Izdeliya-30, or Saturn AL-51, as it is often dubbed in parts of Russia, can only go up to Mach 2, the Russians have come up with a mind-blowing game changer that could open up the possibility of having a multiple propulsion mode, like the turbine-based combined cycle that is being designed for the son of Blackbird. However, Russia has taken it all to the next level. While they are mostly borrowing a play from the United States manual with taking inspiration from the turbine-based combined cycle engine, they have actually been able to settle on a turbofan engine that is supercharged enough to push the envelope enough to hit Mach 4 and help transition the aerodynamics to the scramjet. The United States might have dreamt of it. Still, it would seem that the Kremlin has actually built it. However, just like the son of Blackbird, the Kremlin's turbofan engine definitely requires an aircraft completely capable of carrying it with a scramjet paired to it to achieve hypersonic bliss. Hence the creation of the MiG-41. The Izdeliye-30 was initially developed for the Sukhoi Su-57, Russia's first operational stealth fighter, which can also be used on the ground and for maritime strikes. However, as soon as the United States created their own non-operational hypersonic jets, Russia were desperate to be back at the top of the summit. Hence, they made the Izdeliye-30, which would be forming a part of the Mikoyan Pact DP, or MiG-41, and coupled with a scramjet to achieve Mach 6, hitting hypersonic levels and beyond. However, before the MiG-41 is in production, the Kremlin sanctioned the creation of the Sudakov Su-57M, with reports of it being a possible testbed for the Izdeliye-30 engine, where the thrust vectoring, fuel efficiency, and heat resistance will be tested to the limit before it is used in the MiG-41. The Kremlin has spent billions of dollars on creating the Su-57M, and more has reportedly gone into creating the perfect aerial beast in the MiG-41. While the Kremlin's hope for success cannot be overstated, some may have cautiously wondered why any country squanders billions on a particular aircraft just to see if it is capable of using their newly made engine. So far, it hasn't disappointed. Reports from flight tests of the Sudakov Su-57M were especially promising, creating the needed motivation to continue the MiG-51 project. Even after the evolution of warfare globally, with changes in how it is fought and won, certain aspects of war remain constant. Those aspects include intelligence gathering, stealth, and reconnaissance missions, hence the need for a hypersonic fighter jet, which is equipped with multiple features, particularly for interception. The Kremlin developed the PAK-DP or MiG-41 to be interceptor jets, and for good reasons. While aerial dominance is crucial to warfare, it needs to be focused on in two key areas, both offensively and defensively. However, the MiG-41 was built as an interceptor, a bullish attack dog, ferociously hunting down enemy aircraft in Kremlin airspace and readily equipped to destroy them. At the same time, these jets are tasked with engaging and neutralizing reconnaissance jets and bombers. They are equipped with sophisticated radar and other instruments to locate and track targets. Although most interceptors are fitted with armaments that are geared towards defending against aerial threats, the MiG-41 is equipped with an anti-missile laser, meaning that it could seek and destroy ordnances released from opposition aircraft and still strongly capable of destroying the plane that fired it, a multi-purpose weapon of destruction. While its capabilities in strike and combat missions are impeccable, huge concerns have been raised about the jet's ability to fly at higher altitudes. However, the Russian Air Force believes that the plane could travel at high altitudes between the stratopause and the tropopause, meaning that it could travel above 12,000 meters and below 45,000 meters. Although the aircraft could obviously travel at such high altitudes and do its job as a strike team, the Kremlin decided to equip the jet with an Izdeliye-30 engine with a dual-mode scramjet or ramjet, giving it a chance to go even faster than Mach 6. Alas, the Kremlin has found its way into creating its own version of the son of Blackbird's turbine-based combined cycle, and it is so much better since it already functions. Although the engine gives a Mach 6, rumors suggest that the Kremlin may be thinking of even more speed, with a possibility of spending more billions than they already did on the MiG-41. Although Russia's continuous sanction from the United States somewhat keeps them at bay, making one wonder what else they could have done if they had no economic and financial restrictions. Whether the world continues to watch Russia grow or the emergence of the MiG-41 sparks another arms race remains to be seen. Russia is secretly testing a colossal new war machine unlike anything the world has ever seen. This next-gen beast is designed to break the sound barrier and rival America's top stealth technology, which is rumored to redefine air warfare forever. With leaked footage sparking global alarm and military analysts scrambling for answers, Russia isn't just testing this jet, it's sending a warning. Could this be the beginning of a new arms race? Is the world ready for what Russia is about to unleash? Join us as we reveal the terrifying details of Russia's $13 billion supersonic fighter jet. In 1979, the Soviet Union started planning for a new type of fighter jet that would enter service in the 1990s. This I-90 project aimed to create a multi-role aircraft with strong ground attack abilities, replacing older jets like the MiG-29 and Su-27. After the Soviet Union collapsed, money became tight. So in 1999, the Russian Defense Ministry launched a new project called PAKFA, also known as I-21. A competition began in 2001, and by 2002, Sukhoi was chosen to lead the project. This effort led to the creation of the Su-57. The Su-57 is Russia's first stealth fighter and belongs to the fifth generation of fighter jets. While designing this fighter, Sukhoi considered the American F-22 a starting point, but made changes to improve it. They felt the F-22 couldn't do everything needed, like carrying a wide range of weapons or handling specific flight problems if the thrust vectoring system failed. Sukhoi aimed to build something more flexible and better suited for multiple roles. The jet has a sleek shape, a vast body, and two engines spaced far apart. It has movable wings and tail surfaces to help it stay agile. The wings are shaped like a trapezoid and include several movable parts for control. The Su-57 also uses thrust vectoring, changing the direction of engine thrust, to improve how it flies, especially during sharp moves or stalls. Special surfaces on the wings help control airflow and improve performance at steep angles. To slow down in flight, the Su-57 uses a mix of control surfaces that move in opposite directions to create drag. The plane is made from a blend of strong materials, mostly aluminum and titanium, and many lightweight composite materials. These composites cover most of the jet's surface and help reduce weight while keeping the plane strong and stealthy. One of the Su-57's key strengths is the ability to carry a wide range of large weapons inside its body. These weapons are stored in two central bays beneath the aircraft between the engines, and two smaller side bays near the wings. Keeping the guns inside helps the jet fly faster and more smoothly while maintaining its stealth features. The jet's design allows it to be very agile. It has a naturally unstable structure, on purpose, which is controlled by an advanced flight system called KSU-50. This system and engines that can change direction mid-flight make the Su-57 capable of complex and extreme maneuvers like Pugachev's Cobra and the bell turn. It can even spin flatly in the air without dropping much altitude. The Su-57 can reach speeds up to Mach 2 thanks to powerful engines and innovative aerodynamics. Even more impressively, it can fly at Mach 1.3 without needing afterburners, a feature called Super Cruise. This allows it to strike targets farther away, faster, and with less fuel. With a large fuel tank, the Su-57 can fly over 1,500 kilometers at supersonic speed, more than double the range of older jets like the Su-27. It also has a refueling probe that extends during flight to increase its range even further. As Russia's first stealth fighter, the Su-57 uses many tricks to stay hidden from radar. Like the American F-22, it's shaped in a way that bounces radar waves away from the source. The edges of its wings, control surfaces, and panels are angled carefully to reduce visibility. The jet's weapons are hidden inside, and antennas are set below the surface to keep the sleek look. Special coatings on the body help absorb radar waves, making the plane even more challenging to detect. The Su-57 also uses stealth techniques in its sensors and air intake design. Its infrared sensor, which helps it spot enemy heat signatures, faces backwards when not in use and is covered with radar-absorbing material to stay hidden. To reduce radar reflection from the front of the engines, a common weak spot in stealth aircraft, the jet uses curved air intakes lined with radar-absorbing material. These curves hide the engine blades from radar. Any part still exposed is blocked by a special grid, much like what's used in the FA-18 Super Hornet. Even the cockpit canopy is designed for stealth. It's coated with thin metal oxide layers that absorb radar waves, reducing the cockpit's radar visibility by 30%. This coating also protects the pilot from UV rays and heat. To boost its stealth even further, the Su-57 is built with much tighter tolerances than older Russian jets, meaning its surfaces fit together more smoothly to reduce radar reflections. The Su-57's current propulsion system, the AL-41 Phone engines, delivers powerful thrust and advanced maneuverability, especially when paired with its thrust vectoring nozzles. These engines are a significant upgrade over previous Russian power plants, offering around 14.5 tons of thrust in afterburner and up to 15 tons in emergency mode. Full Authority digital engine control integrates these engines directly with the flight control system, allowing smoother transitions, greater stability, and precision handling during extreme maneuvers. The engine inlets are also smartly designed for both high-speed flight and rugged operations. Variable ramps adjust airflow during supersonic flight, while retractable mesh screens protect the engines from debris, which is especially useful when operating from improvised or damaged airstrips. However, Russia is still developing a next-generation engine, the AL-51F1, also known as Izdeliye-30. This engine, expected to become standard with the Su-57M variant, will produce more thrust, up to 17 tons with afterburner, improve fuel efficiency, cut costs, and enhance stealth using composite inlet guide vanes and a specially designed nozzle. A key feature under development is the flat nozzle, which reduces the jet's infrared and radar signature from behind, one of the Su-57's current weaknesses. This new nozzle began flight testing in late 2024 and is designed to integrate with the current airframe with minimal modification. The Su-57 has an internal weapons configuration to preserve its stealth profile during combat operations. It features two tandem central internal weapon bays, each approximately 4.4 meters long and 0.9 meters wide, capable of carrying a variety of heavy munitions. In addition, the aircraft has two smaller side weapon bays located near the wing roots, which are designed for quick-launch, short-range missiles. These bays are equipped with specialized launchers. The Vimpel UVKU-50L, used for rockets weighing up to 300 kg, the UVKU-50U for ordnance up to 700 kg, and the VPU-50 launch rails, which are used in the side bays for lighter weapons. For air-to-air combat, the Su-57 carries a mix of medium and short-range missiles internally. The central bays can house up to 4 beyond visual range K-77M missiles, which are upgraded versions of the R-77. These feature an active electronically scanned array radar seeker, a dual-pulse motor for extended range, and redesigned aerodynamic surfaces. The side bays carry two R-74M2 short-range infrared-guided missiles, which have been specifically modified with a reduced radar cross-section to allow internal carriage. Russia is also developing a new rocket, the KMD, as a next-generation replacement for the R-74M2, with expected agility and sensor fusion improvements. Regarding long-range engagements, the Su-57 is compatible with the Izdeliye-810 missile, a more compact development of the R-37M long-range air-to-air missile. This missile has redesigned control surfaces and an updated propulsion system, allowing it to be carried internally, 2 per bay. The standard R-37M can still be carried externally when stealth is not a priority. For air-to-ground missions, the Su-57 can carry several types of precision-guided munitions. These include the KAB-250 and KAB-500 bombs, weighing 200 and 500 kilograms, respectively, which are designed for precision strikes. The aircraft also supports a diverse missile loadout, including the Kar-38M tactical missile, the Ka-35U anti-ship missile, the Ka-58 UHK anti-radiation missile for suppression of enemy air defenses, and the Kh-69 cruise missile, formerly known as the Kh-59 Mk2, which is optimized for stealthy standoff attacks. Additionally, a new hypersonic missile is under development for the Su-57. This missile is reportedly similar in performance to the Kh-47 M2 Kinjal. Still, it is being designed with smaller dimensions and intra-body integration to allow internal carriage within the Su-57's central weapon bays. further enhancing its stealth capabilities. The aircraft is also armed with an internally mounted 30mm 901-4071K autocannon, a modified version of the GSH-39-1. This gun is located near the right leading-edge vortex controller and carries 150 rounds. It has an effective range of approximately 800 meters against aerial targets and up to 1,800 meters against surface targets, making it a versatile weapon for dogfighting and ground attack missions. On 25th of December 2020, the Russian Defense Ministry announced that the Su-57 had officially entered service with the Russian Air Force following the delivery of the first production aircraft. This initial aircraft was assigned to an aviation regiment in the Southern Military District, based in Lipetsk. The early production batch was designated primarily for military evaluation, operational tactics development, crew training, and conversion to the new platform. The first operational combat unit to be fully equipped with the Su-57 is the 23rd Guards Fighter Aviation Regiment in Jomgi within the Eastern Military District. Deliveries to this unit began in 2023, with the regiment's proximity to the Komsomolsk-on-Amur aircraft plant offering logistical advantages for support and integration of the new aircraft. Russia has stated that a complete regiment of 24 Su-57s will be operational by 2025. The Su-57 has reportedly seen combat service during the ongoing conflict in Ukraine. On 19 October 2021, Russian Army General Sergei Surovikin, then commander of all Russian forces involved in the war, claimed that the Su-57 had been deployed in both air-to-air and air-to-ground roles and had achieved kills in both. According to unverified Russian reports, the aircraft shot down a Ukrainian Su-27 using a long-range R-37 missile. However, independent verification remains lacking despite these assertions, and no conclusive evidence has emerged to confirm combat kills. Several Su-57s remain stationed at Lipetsk and Akhtubinsk air bases, primarily involved in development and trials. Satellite imagery from December 2022 confirmed the presence of 5 Su-57s at Akhtubinsk Air Base, located approximately 500 kilometers from the Ukrainian border. In May 2024, Ukrainian sources reported an uptick in Russian Su-57 sorties targeting Ukrainian territory. These airstrikes were reportedly launched from Russian-controlled airspace over Kursk, Bryansk, and the occupied region of Luhansk. The strikes employed the latest Ki-69 stealth cruise missiles, highlighting the growing operational role of the Su-57 in long-range precision strike missions from standoff distances. While other countries are still trying to stop the Su-57, Russia has moved ahead with something new. In 2021, Russia showed off a non-flying model of the Su-75 Checkmate fighter jet at the MAX Air Show, with President Vladimir Putin attending. This jet was first supposed to fly in 2023, but that was pushed to 2024 and now to 2025. If things go as planned, deliveries might begin in 2026 or 2027. The Checkmate is meant to be affordable and aimed at countries looking for a cheaper fighter jet. It's built to compete with planes like the US F-35 and China's FC-31. Russia hopes to make around 300 aircraft over the next 15 years. Each plane is expected to cost between $25 and $30 million. As for design, the Su-75 includes features that help it avoid radar, like a special air intake and hidden weapon storage. Its large wings suggest it's built to fly high, possibly above 40,000 feet. The Checkmate's unique air intake design wraps around the lower nose and follows a more straightforward style called the diverterless supersonic inlet. This design, which was first seen on the Boeing X-32, helps cut costs and weight compared to older, more complex systems used in jets like the F-15 or Su-27. Instead of a regular tail, the Su-75 uses a V-shaped tail similar to the one found on the Northrop YF-23. This V-tail uses a combined control surface called rudder vaders that handles up, down, and side-to-side movements. However, because these are more complex to control, the jet needs a more innovative flight control system to manage them. The Checkmate is expected to fly up to 3,000 kilometers without refueling, carry about 7,400 kilograms of weapons, and hit speeds close to Mach 2. It will have an internal bay with 5 missiles and a gun, keeping weapons hidden to reduce radar visibility. In 2023, patent documents showed that the jet's body was updated. Changes to the sides, air intakes, and other parts were made to help it stay off radar. The updated shape also seems to give the jet more lift. The engine will likely be the Saturn Izdeliye 30, the same one planned for the upgraded Su-57. This engine is lighter, more efficient, and has more vigorous thrust than older models. It also promises a longer working life, which could make maintenance easier over time. Though no photos were allowed inside the cockpit, a journalist who saw it described it as very similar to the Su-57. It features a modern glass cockpit with 2 large LCD screens and a wide-angle head-up display that helps the pilot keep track of critical flight information while staying focused on flying. The Checkmate's electronics are built on an open system, which means upgrades and fixes can be made more easily. It also uses an onboard diagnostic setup called Matryoshka that helps detect problems without needing external tools. To keep costs low, a new affordable ESA radar is in the works, and many of the jet's parts and systems will be shared with the Su-57, according to government officials. This approach helps cut development time and spending. Russia isn't stopping with the Checkmate. Work is moving fast on the MiG-41, a 6th-generation fighter meant to take over from the older but mighty MiG-31. This new jet aims to push into high-altitude and even near-space flight. That's right, Russia plans for the MiG-41 to fly at the edge of space. The MiG-31, known as the Foxhound, could reach speeds near Mach 2.8 and carry massive long-range missiles like the R-37. The new MiG-41 will aim to be even faster and wiser. All its weapons will be hidden inside to reduce radar visibility. Russian sources even claim the jet will include technology never seen before in any fighter. Known as the PAKDP program, this project is focused on creating a super-fast, stealthy, high-flying interceptor. The goal is to launch it sometime in the 1930s. The design was reportedly completed in late 2019. MiG's top boss, Ilya Tarasenko, confirmed in 2020 that the MiG-41 will be a new jet built from scratch, not just an upgrade of the MiG-31. It's expected to fly at speeds beyond Mach 4, feature a laser system to shoot down missiles, and be capable of flying extremely high, possibly between the tropopause and the edge of space. The MiG-41 is set to build on the MiG-31M's technology with an advanced Zaslon M radar for improved tracking and targeting. It might also use a version of the Izdeliye 30 engine currently being developed for the Su-57. The R-579-300 engine is another option that could work well for this fighter. One of the biggest challenges for the MiG-41 is the pulse detonation engine. This powerful engine must handle extreme forces, making its durability and maintenance a key issue. The PAKDP will also incorporate stealth tech to stay undetected by enemy radar. An exciting addition to the MiG-41 is Russia's development of an electromagnetic pulse gun. This could revolutionize aerial combat, allowing the aircraft to turn off targets at greater distances. Russia is aiming to equip the MiG-41 with an EMP cannon by 2025, with a less powerful version possibly used for taking down drones. The MiG-41 might also carry the powerful R-37M missiles. In the future, the MiG-41 could even have an unmanned version. Suppose the MiG-41 makes its first flight by 2025. In that case, analysts expect it to be fully operational by the early 2030, rather than the original target of 2023. Apart from its latest fighter jets, Russia is also working on bringing back an old project with a fresh purpose: the Okhotnik, a large unmanned combat drone. Work on the Okhotnik began around 2011, when Sukhoi was chosen to lead the development of a new heavy drone that could handle both spying and attack missions. This drone is a joint effort between Sukhoi and MiG, using earlier research from the McCoy and Scott project. The aircraft is being built by the Novosibirsk aircraft plant, which is part of Sukhoi. In September 2019, Russia released a video of the Okhotnik flying with the Su-57. The drone flew independently for over 30 minutes, working closely with the fighter jet. This test showed how the Okhotnik could help extend the Su-57's radar and allow it to fire long-range weapons from safer distances, far from enemy defenses. By early 2021, Russia had begun building 3 more Okhotnik prototypes. The second model was slightly improved from the first, while the third and fourth were made to match what the final production version would look like. These newer versions featured better onboard electronics and changes to the drone's structure. One big improvement was a flat engine nozzle, which helps reduce the drone's heat signature and makes it harder to detect. In February 2021, it was reported that future Russian warships, specifically the Ivan Rogov-class amphibious assault ships, could carry up to 4 Okhotnik drones for spying and attack missions. The Okhotnik has a flying wing design with no tail and a smooth shape to reduce how easily it can be seen by radar. It's made using special materials and coatings to help it stay hidden while flying. The drone weighs about 20 tons and has a wingspan of 20 meters. It's powered by either the AL-31F engine, used in older Russian fighters, or a newer version called the AL-41F. Its top speed is said to be around 1,000 kilometers per hour, and it carries its weapons inside the body to stay stealthy. This aircraft can carry up to 2,000 kilograms of bombs and missiles inside 2 internal weapon bays. This includes both freefall bombs and guided weapons. With these advanced jets, Russia isn't just securing control of its skies, it's gearing up to strike deep into enemy territory and unleash total chaos on its rivals. Thanks for watching. While you are still here, click on the link appearing on your screen to check out another of our videos. See you there.